Hi everyone, welcome to another AI session. So today we will be talking about an interesting stage in the training process of large language models, more specifically models that generate visual content, for example, images or videos. Now, I believe we've all heard of the groundbreaking Sora release, which is a new model by OpenAI that generates stunning video content. And I have been going through their report for quite some time now, and I found one interesting stage in this entire training process that I just wanted to practice and talk about. So this stage right here, so I have coined the name to be patchnization. So it's a stage that is that involves getting the video content into integers in this case. So this has been done with other network like convolutional neural network and so on. These have been the most popular architectures for this kind of task. But lately, transformer models have proven quite efficient in training visual data as well, not only text. So this stage right here, which I have coined name patchnization, so it involves getting this video content, the video content, into a data that the transformer understands, because the transformer, as we all know, just eat up a bunch of matrices, right? So, and these matrices, they are made up of integers and so on. So I have been able to play around with it for a while now, and I managed to come up with a simple implementation that involves getting a video from that visual data to linear embeddings, or to integers, to a sequence of integers. So this is the code. I've already published it. I named it minbpe, and it is actually inspired by Karpathy's implementation minbpe. So you can tell by the name there. Yeah. So basically what this code does is it first extract images from a video. So suppose we have a video, we extract images or image frames. So each frame, we know that a video is just a bunch of images at different frames, right? And so on. And then next, it splits the images into smaller fixed patches or smaller fixed images. So we cut those frames into smaller fixed size images. And then next, we apply a linear embedding to those images. That is, we convert the pixels in those images into integers. And then we add position embedding, which we'll talk about later in the video. So there are like 4 basic files in this entire repo. So we have the patchnizer, which just holds the basic implementation of the 3 stages involved. And then we have the patchnize, which actually performs the whole process. And then we have a train, which trains this one-dimensional vector space sequence, sorry. And then using Karpathy's minbpe. And then the last one is check.py. This one just verifies whether what we've patronized, whether the embeddings, the linear embeddings we've created, they match the original pixel images. So this will just convert the embeddings or the integers back into images. Okay, so in order to see this in action, let's try to run the entire code first. So for example, the first stage will be to run Python, and first we have to run patchnize, so this file right here, patchnize.py. So what this will do, it will, there are, okay, inside of the patchnizer class, there are like 3 main functions. So the first one, like I've mentioned, it extracts the image frames, so still images of the video. So for example, here I have the video here. Where is it? It should be in test. Yeah. I have the video, which is one of the videos generated by Sora. So this video of these dogs playing in the snow, and I'm trying to get this actual data to be readable for a transformer. And in order to do that, there's this stage called patchnization, which is a word I've coined, as I've mentioned. So this stage just gets the frames in this video, the image frames. It splits them into smaller images, and then we then convert those images into integers, and then from there we can add, let's say, some indexing to those images, and then add that to the original sequence of integers that we've created. And then we can use this to later train a vision transformer like the one they used for the Sora model, basically. So yeah, so this is the video here. So this image actually explains it much better, the image from Sora itself. Let me see here. Okay, yeah. So these are the frames, these are the image frames, and then when we pass them through a visual encoder, we get this huge matrix, right? For each frame, we get a huge matrix. For example, this frame, this matrix, as you see here, represents for this first frame and so on. But what we want to do is to linearize this entire block. So we linearize it into one dimensional space, so that this data can be fed into the transformer for training and so on. Yeah. So basically, that's the whole process involved here. So as we can see here, as I've run the code, so it took about 16 seconds to do the entire process. So the 3 stages: extract the image frames, and then we chop those image frames into smaller images. That took 13.89 seconds, and then we'll apply linear embedding, which is to turn those images, those smaller images, into integers, right? And so on. So if we look here, we can see the various folders that were generated when this code ran. So first is a video frame. So here, these are the frames, for example. These are the frames of the video, as you can see here. Let me try to open it here, and then let's do some, okay. Yeah. So I'm trying to do the old school film kind of thing. So in old school, the film has pictures, that frames of the movie, right? And then there's a machine that, I don't know how it works, but it just scrolls through those images faster. I'm not gonna be able to do it faster here, but this one should work. So if we can see clearly here, you can see the images. You can see, yeah. So basically that's it. So you can basically see the video in this case. Okay. Yeah, so these are the frames, okay? And then next, what we did, we cut these frames into smaller patches. So for example, this first image that you see here, this first frame, we chop it into smaller patches, just as shown in the transformer paper here. We chop it into smaller patches. So these are generated in these are generated in image patches folder. So for each frame we have it. So you can see there's a small size. So this might probably match to, let's say, the first, yeah, maybe some part around here where you have like a white kind of snowy thing. So this part will match to that, and so on. So we get all these smaller patches, and then we save them for each frame, as you can see here. And then next, for each frame, we apply the embedding. That is, now we convert this particular small patch into an integer, or a 16 by 16 pixels integer in this case. So that will be a long matrix. So for example, this one you see here will represent for the first frame. that we already patchnized. So this will be the resulting integers for that. So this is basically the image for that particular section. Interesting, right? Okay. So that's the whole process for the patchnization. So this process actually is very important in trying to get the transformer to, to train these models. So as you can see here, this was actually introduced by this paper. An image is worth 16 by 16 words, which was released by Google. They are known for releasing all the transformer. As you can see, this is a vision transformer. So basically, this is what we've done here. So this is, for example, an image frame from the video. And then you can see it is chopped into smaller patches. And then these smaller patches are then projected linearly here. So they are like given linear projection, they are flattened and then into a single matrix. And then we add position embeddings to those, as you can see in the code here. So in Patchnizer class, yeah. So this is where we're linearly applying the embeddings here, position embeddings, and then we concatenate those two just that we can get a resulting matrix that matches that particular image we are trying to patchnize. Okay. So basically that's how that one works. And then the next stage that I tried, because I've been thinking about this for a while now, so this paper actually shows that the tokenization process for image and text are not so different. So they are basically the same. So they are treated the same in this case because they are both integers for the transformer. So I've been trying to get, let's say, like Karpathy's minbpe, which is a byte pair encoder. So I've been trying to use this encoder to actually train tokenizer to train the tokens that are generated from this one. So if we try that, for example, say that'll be Python and Karpathy's on, okay, that'll be train.py. Yeah. So for those of you who have followed Karpathy's video, you will see this same kind of output when you try to train for a text. So presently I am training this for, let's say, a single frame of an image. So as you can see here, we're getting for each sequence of integers here in our first frame. Where's the first frame? Patch embeddings, yeah, here. So for example, for all these files inside this first frame, so we are getting all these integers and then training our BPE, a byte pair encoder, on that. As you can see, this one took around 32 seconds. It can get shorter than that sometimes. It can get lower than that sometimes. So this is fairly good. And then the models are then generated here. So this is our trained model. So this can be fed into a transformer and used probably for image classification or for video generation, as we've mentioned. So I just wanted to share this with you guys. I think that's all for this video. So the repo is out there. You can go and then play around with it. If you have any contributions, you're welcome to do so. And don't forget to leave a star or raise an issue, whatever. So thank you. That's all for today.